Today, we are going to take a look at the daily returns of stocks and equity indices. I would like to demo some basic quantitative analysis of daily returns. This will be very basic, but as with every subject, the basics often are the most important in understanding the whole subject and form the foundation of more advanced concepts. The price moves of a financial asset are, of course, a very big topic. In fact, you can argue that it's everything that trading or even investing is all about. We will need to take baby steps towards a fuller understanding. I will use the so-called FAANG stocks as examples of single name stocks. These are Facebook, now rebranded to Meta, Amazon, Apple, Netflix, and Google. We will also look at some equity indices that are baskets of stocks. For some baskets, we will use ETFs as proxies for convenience. We're going to look at SPX, the US Large Cap Index, NASDAQ, the US Tech Index, Russell 2000, the US Small Cap. We will also look at MSCI, Emerging Markets and Developed Markets Indices. For those, we're just going to look at the corresponding ETFs tracking those indices, which are denominated in US dollars. We first will look at some of the basic statistics: the standard deviation, the kurtosis, which tells us about fatness of the tails, the VAR, value at risk. In this context, it's a synonym to downside quantile and tells us about the downside risk, but also the symmetry or asymmetry of the distribution and the tails. After that, we will try and see if we can find a good probability distribution function that may fit the returns. Can a normal distribution be a good fit? Or do we need something else with certain non-Gaussian properties? For our purposes, we're going to use Python 3. And for demo purposes, we're using a Jupyter Notebook here. All right, let's get started. First, we import the modules we will need. We are going to use NumPy and Pandas for basic numerical analysis, which are the most commonly used for numerical packages in Python. We're going to need something more advanced to fit a probability distribution function to the returns. We will use SciPy's stats packages for statistical distributions and maximum likelihood fitting. Although in general, SciPy is actually not as well written or maintained as NumPy or Pandas, part of the reason being it's trying too many things, and the different modules are written by different people. So the quality is not very homogeneous. However, it has some well-written packages within, such as this stats module. As always, remember to add some comments to make your code more readable. For visualization purposes, we will be using the matplotlib package. Again, it's the simplest but also a very powerful visualization package in Python. There are many other more advanced packages out there, which will be topics in the future. Here, I'm adding this line, percentage symbol, matplotlib, inline. It's a magic function that renders the figure in a notebook, which is super powerful. We will also need to download the actual history of the stocks and the equity indices and ETFs. We will use the package yfinance to download the history from Yahoo. As we mentioned in another video, a better solution is actually to build a database first, and then just read the history from the database locally, because you don't know when Yahoo may stop providing these free services. But for demo purposes, we're going to use this yfinance package. We will save the history into a CSV file here just to demo how you can do something simple to avoid downloading the data again and again. Finally, we may have forgotten some modules that we may need later. So here we'll leave some room for whatever additional modules we may need later, just in case. Okay, finish up this block of code, Shift and Enter. We imported the modules shown above. Now let's define the list of stocks and the list of indices we're going to study. For stocks, the tickers in Yahoo Finance are just their listed names. Pretty straightforward. For indices, Yahoo has some special symbols defined per their own convention, most of which have a leading hat symbol. Let's write down the list first, then I'm going to provide the mapping. You should go to Yahoo Finance website and confirm these mappings. GSPC is the SPX large cap. DJI is the Dow Jones Industry Average. IXIC is the NASDAQ Composite, the US Technology Index. RUT, Russell 2000, is the Small Cap Index. EEM is the BlackRock iShares Emerging Markets ETF. And EFA is the BlackRock iShares Developed Markets ETF. Okay. Next, we are going to use Y Finance to download the history. Since we are downloading the data for a list of stocks and indices, we should, before more analysis, at least look at one example first and think how to organize or structure the data so it's easier to manipulate and analyze. This is actually the same as we have seen in another video, but for completeness, I will describe it here again. Let's first download the history of Apple stock, AAPL. We'll use the history from 2018 to 2019 as an example. First, we define a ticker instance in Y Finance. Then, we'll call history the history method with start date, the last day of 2017, and end date, the last day of 2019. We need to set auto adjustment to false so we can download the actual history prior to dividend adjustments. Note the close will still be adjusted for splits, which in fact makes it more convenient for the user, so we don't have to apply multipliers for splits and merging histories. We're going to take a quick look as well. It's always good to print out some key values or just graph the data, at least for sanity checks. Okay, let's Shift Enter to run this block of code. Note in Jupyter Notebook, if you hit Shift and Enter keys together, you run the code in that cell. Okay, here we go. We are looking at the first and the last values of the Apple stock in this period. We started from the last day of 2017 and ended at the last day of 2019. We see open, high, low, close, adjusted close, volume, dividends, splits. Adjusted close will be what we need to use later for daily return analysis. They look all good. As we mentioned in another video, ideally we should cross-validate the data with another data source other than Yahoo Finance to assure data quality and integrity. But let's skip that step here. Now that we know the structure of the price history data from Yahoo Finance, We should proceed to download the data for all the stocks and indices. We will start from May 2012. This is just for simplicity and to keep everything consistent, because that's when Facebook went IPO, and prior to then, there was, of course, no data for Facebook, since it didn't exist. Usually, the more data, the better, for more complete analysis and more robust backtesting. But we don't want to confuse ourselves here with different histories for different stocks, just for our demo purposes. Note here, we will only need adjusted close. What we are going to do is to download the history for all the stocks, but only to keep the adjusted close. We will show how to do this and how to combine all the closes into a pandas data frame. First, we'll define an empty list as a container to keep all the temporary histories. We're going to use a for loop to go through the whole list of stocks. Here is the same as the Apple example above. We define a ticker instance, then we call the history to retrieve the data from Yahoo Finance with start date May 2012 and end date, let's say set it to the last day of November 2021, a few days ago, and auto adjust false. Now, as we said earlier, we are keeping only the column adjusted close and dump all the rest. We will need to rename the column name, and the pandas makes this pretty easy for us. We'll just call rename and give the columns argument, which is a dictionary. And we map old column name to new column name, which is the stock name itself. And then we're going to append this stock's close history to the list. After the for loop, which will download the histories of all the stocks on the list, we will call pandas concat to merge all the histories. We need to set axis to be 1 here to specify we want to match them by the date index along the columns. So we are appending each new data frame horizontally, but not vertically. Now we do the same for the indices. We're going to query for the history in the same period for all the indices defined above. In fact, let's just copy and paste the code above. But let's change all the stock in the names to index to distinguish them. This is actually not a good practice to have repetitive code. Better way to is probably to think of something more modular, tight and concise. But I'll leave that to you to figure out. Okay, stock to index, stock to index. Okay, now we have everything. Shift and enter to download all the data. Everything looks good so far, no error. But we need to make sure we are doing everything right. So let's do some sanity checks. Let's print out the first and last values for the two data frames. Actually, let's also print out some comments so that we know what we are looking at. Here we go. The first date is May the 31st, 2012. And the last day is November 29th. They look alright. In fact, we should cross-validate the data with another data source. But again, let's skip that step here. Now, let's save the data into a CSV file because we may want to run this again and again. And we don't want to run the query to Yahoo Finance every time we run it. In fact, Google Finance used to provide free data as well, but then they disabled it at some point. Yahoo may do the same in the future, or they may just block you if you run too many queries within a time window. Pandas makes this super easy. Just do to underscore CSV, and we have it. Note here, I'm not giving any path, so the files are saved in the current directory as the notebook. Okay, now that we have saved the data into the CSV files, we can just read out the data from these files. Consider them the simplest, most naive database you just created. We use pandas read underscore CSV to read out the data. Let's give a suffix 0 to make sure this has a different name. Note we should specify the column for the index, which is the first column with index underscore col 0. And we know the index is dates, so we should set parse dates to be 2. Okay, let's do the same for the index data with suffix 0. Use read underscore CSV index col 0 parse dates 2. Okay, let's read out the data. And again, we should perform some sanity checks. Let's print out the first and the last values again to make sure everything is good. They should be exactly the same as what we saw earlier. 29, 338, 29, 338, 1310, 46, 55, 1310, 46, 55. Very good. Let's continue, and we will just use these new data frames. So in the future, we don't need to re-download the data as long as that's what we are going to analyze. We have only done some really simple sanity checks. Before we proceed to the statistical analysis, we should graph the data and get a first impression. We're going to use the matplotlib package. Let's define a figure size that's larger than the default, 12.8. You can change the default figure size as well. The documentation of matplotlib is pretty thorough, and you can learn how to do that. Let's set the titles for x-axis, y-axis. Let's create a for loop to plot the history for one stock at a time. You can use pandas plot method to plot them all together as well. But here, we'll use for loop. Finally, let's add a legend to make sure we can tell the stocks apart. Okay, here we go. We see Amazon is the most expensive per share. Then it's Google. You probably know that. You cannot really compare the absolute price of different stocks because it depends on how many shares each company issues and the value of that company. What we should do is to plot the relative returns normalized to the start date for an apple-to-apple comparison. So let's graph them again. But this time, we normalize them by the values on the first day. What it means is if you put in $1 on the first day in each of these stocks, what you are going to end up later, not including the dividends. We just copy and paste, but here we do the normalization by the value on the first day. Let's also print out the value on the last day, normalized, to see how much $1 has turned into on the last day. Here it is. Are you shocked? Netflix stock has increased to 73 times that on May 31st, 2012. That means if you put $1,000 on May 31st, 2012 into Netflix, you'd have $73,000 now. That's pretty good return. Others have done pretty well too. Even the worst one, quote on the worst, Apple, still generated over 800% return. That's pretty decent. We can do the same for the indices. Graph the normalized returns and see how much $1 would have turned into if we had put it into each index, a basket of stocks. Let's just copy and paste the previous block of code. Then we're going to rename all the stocks to indices. Stock index, stocks indices, stock index, stock index, stocks indices. Okay, shift and enter. Here we have the total returns of indices since May the 31st, 2012. It's probably not surprising that NASDAQ, the technology index, did the best. We would have over $5,000 now if we had put $1,000 in NASDAQ on May the 31st, 2012. The emerging market ETF has performed the worst, but still generated positive returns. Okay, these graphs give us some first impressions of these stocks and indices. Let's move on to investigate some of the basic statistics of these price histories. For statistics, we are going to look at daily percentage returns. You may have also heard of logarithmic returns, which could be useful for certain applications. But most of the time, percentage returns are what people are focused on. We will look at standard deviation and tail statistics. And we will also compare the daily return distribution with normal or Gaussian distribution. We need to calculate the daily percentage returns first. Pandas makes this very easy. What we need to do is just call the percentage change method. Note here, we feed forward if there's any missing data on a given day. So on those days, percentage changes would be just 0. Adding a comment here. Let's do the same for the indices too. Note I'm discarding the first data point here since the percentage change on the first day has no meaning. And I post this question here about logarithmic returns. In case you are interested, you should do some research and see in what situations logarithmic returns are useful. Okay, shift enter. We have the daily return data frame. Okay, now we're going to calculate the standard deviation of the daily percentage returns of all the stocks and indices. Here, I'll do something slightly more clever so that we don't need to copy and paste like what we were doing earlier for the indices. I'm using this zip function, which returns a so-called iterator. What it does here specifically is to take two lists matched in length and return the elements in both, one at a time. So for asset type stocks, the temp DF is stock daily returns. And then for asset type indices, the temp DF is index daily returns. We then use the std function in pandas to calculate the standard deviation. But note here, we need to set axis 0, so it's calculated along the index axis for all the columns. We also multiply it by 100 to show the percentage. Alright, adding empty line here at the end for clarity. Shift and enter. We just printed out the standard deviations of the stocks indices we're investigating in this period. For the FAANG stocks, we see Netflix has the largest volatility with daily standard deviation 2.9%. Then it's Facebook or Meta. Apple and Google have similar smaller fluctuations, 1.77 and 1.59%. The standard deviation of the indices are smaller. This should be expected since they are baskets of stocks with a high degree of diversification. We see NASDAQ, Russell, and emerging markets are relatively larger, but still only 1.2-1.3%. SPX, Dow Jones, developer markets are even lower, at only 1.04-1.05%, very close to 1%. Some of you may know about CAPM, Capital Asset Pricing Model, and then these numbers may be familiar to you because you need them for beta calculation. Next, we will take a look at the distribution of daily percentage returns. We will plot the histogram of the returns first, and then compare it with normal distribution. Let's define the figure we want to plot using matplotlib's subplots function. Here, 1 and 5 mean 1 row and 5 columns, since we are plotting the distribution of 5 stocks. We will also have all the 5 subplots share the same y-axis to make the figure tight. Also, let's define a long figure to fit in all the subplots, since we have 5 columns. We will see what this means later. Since the 5 subplots will share the y-axis, we are going to set the horizontal space between them to be 0. Again, this is to make the figure look tight. You should resort to the matplotlib documentation to learn more about this. It's pretty thorough. Now we are going to use a for loop to loop over the stocks. Note here, we are introducing a new Python function enumerate. Similar to the zip function earlier, it returns a so-called iterator, but different from the zip function above, which takes in multiple arguments. Here, it takes in just one, but returns the number and the element, basically the enumeration. For each stock and each subplot, we use the hist method to plot the histogram. I'll write down the options and then explain what they mean. Here, density means the histogram is normalized to percentage instead of just numbers. Alpha means transparency, so the histogram is not completely covering other lines you may want to plot. Range is the range we are plotting the histogram for. Here, I'm setting it to minus 11% to 11%. And bins means how many bins within that range we're calculating the statistics for. And we're going to set the title for each subplot so that we know which is which. Finally, we're going to compare the distribution with the normal distribution. We're going to just use the mean and standard deviation as the parameters of the normal distribution, which in fact is the maximum likelihood estimator of those parameters. We here define a temporary x variable, 100 data points, evenly distributed between minus 11 and plus 11%. Then we are using SciPy's stats norm package, norm for normal distribution. We're calling it PDF, and use the daily returns, mean and standard deviation as the parameters. Actually, it's a really bad practice to define single character variables. Let's add a temporary prefix in front of it. Maybe it's better to name it specifically like norm underscore x, but for now, this will do. Next, plot the normal distribution we just created in this subplot. Axis I in black. Set the line width slightly bolder for better contrast. Also, let's move this temp x line outside of the loop since it's common for the whole loop. Okay, let's shift and enter. Go. There's a bug here. Forgot to update this one. Should be temp underscore x, not x. Here we go again. We see a figure with 5 subplots horizontally distributed, with shared y-axis and no space in between, as we set up earlier. We can see for none of the 5 stocks, normal distribution matches the distribution well. They are peakier and have fatter tails compared to Gaussian distribution. Remember Netflix has the largest standard deviation? We can see it's broader here as well. Let's do the same for all the indices. We're just going to copy and paste the code above. Control C, Control V. And then we're going to rename all the stocks to index and indices. Stock index, stocks indices, stock index, stock index. Forgot one here. Okay, let's run this block of code. And this is a bug. Well, there's 6 indices compared to 5 stocks. We need to update this figure definition. We need 6 columns here. We should have just used the length of the list of stocks and indices. Anyways. Shift and enter. We see a figure with 6 subplots horizontally distributed with shared y-axis. The normal function looks like matching the distribution slightly better compared to the stocks, but the distributions are still peakier and have fatter tails. How do we quantify the fatter tails compared to the normal distribution? We can calculate the kurtosis and quantiles. For kurtosis, remember for normal distribution, the value is 3. We can also use excess kurtosis, which is kurtosis minus 3, to quantify the fat tails. We're just going to follow what we did with standard deviation earlier. Use a for loop and the zip function, but change the std function to kurtosis function, also with axis 0. Basically the same as what we did with standard deviation above, just with one difference, kurtosis replacing HTD. Okay, calculate. We see Netflix has the largest kurtosis, while Apple has the smallest one, closest to normal distribution. The indices actually have pretty large kurtoses, so by this metric, they are pretty far from normal distribution, unlike the impression we had earlier. Now we can look at quantiles, basically one-sided tail statistics. If you know the concept of VAR, value at risk, this is the same as VAR if you are long each of these stocks and indices. They tell you the downside and the extreme downside risk. Let's just copy and paste what we did above, but change the kurtosis function to quantile function. And we're going to set argument to 1%, 2%, and 5%. We see Netflix has the most negative returns for all 1%, 2%, and 5% quantiles, consistent with the larger kurtosis and the fatter tails we concluded above. For the indices, NASDAQ and the Russell and the emerging market have larger quantiles, even though Dow Jones have the highest kurtosis. Remember, these indices have a larger standard deviation, which is the reason. This is also why we need to look at multiple metrics for a more complete view of the distribution. Each metric is telling us something different. A few more words about VAR, value at risk. 1% quantile is the same as VAR 99 if you are long this asset, meaning there's 1% chance you will be losing more than that amount. So it tells you the downside or extreme downside for 1% risk. 5% means VAR 95. Value at risk is one of the most important concepts in portfolio analysis. So look it up and you can learn more about it. Above, we've already compared the normal distribution with the daily returns, and we've seen that the Gaussian function is not a good PDF for the distribution. You may have already known that the arithmetic mean and standard deviation are the maximum likelihood estimators for the mu and sigma in the Gaussian distribution. But let's do the maximum likelihood fitting here more formally with the SciPy stats package, which we used above to make the plot already, but we'll use the fitting function in it here. You can follow this link to find the documentation of the norm module. The documentation is quite detailed, and I recommend you to take a look there. The structure of this part is similar to above. We're going to use subplots to plot the distribution and overlay the best fit Gaussian function. As what we did earlier, set one row, 5 columns for 5 stocks, share y-axis, set a horizontally wide figure, and then adjust the space in between the subplots to be 0. We're using a for loop to loop over all the 5 stocks, using the built-in enumerate function again. For convenience, we are defining the temporary return series here. And here we call stats norm fit, which will perform maximum likelihood fitting to the series and return the best fit, mu and sigma. To plot the daily return distribution, let's copy what we did above to plot the histogram of the daily returns for each stock. Let's go up here, copy this line and paste it here. We just need to replace the direct call with the temporary series we defined above. Set his type to be bar stacked in case we want to plot multiple series. Actually, this is not necessary. Sorry about that. Now, same as above to plot the best fit PDF, we define a temp x from minus 11% to plus 11% with 100 data points. Move it outside of the loop since it's shared. Now use norm PDF to return the probability at temp underscore x. And then we are going to overlay this best fit function in the current subplot. Let's add a title here to show the best fit parameters. We are using formatted string here. The $sign means it's latex text inside, which is useful to write Greek symbols and formulas. Mu and sigma with backslash. I just realized that I use HTD instead of sigma, but usually they mean the same thing. Now call set title. Also, let's add a legend using this text function to show what is the stock the current subplot is for at the right positions. Here it is. The fitting is pretty fast, which is nothing extraordinary since the sample size is pretty small. The black lines are the best fit Gaussian functions overlaid on top of the daily return distribution. Pretty much the same as what we saw earlier, but done more formally with the fitting function here. We see Netflix has the largest best fit sigma, as we have already learned above. And the daily return distributions are just too picky for Gaussian function. Next, we'll do the same for the indices. I'm just gonna copy and paste this code for stocks, and then rename all the stocks to indices. Stocks indices, stock index, stocks indices. Everything else is the same. Shift and enter. That's a bug. And the same mistake as before. There's 6 indices, not 5. Try it again. Here we go. The title is a little too big. Let's make it smaller. Not a legend. It is a little too small. Let's change it to 12. Here we go. Looks good now. We see that the standard deviation for Russell emerging markets, NASDAQ, are higher than developed markets, SPX, and Dow Jones, as we saw above already. Again, normal distribution is not a good fit, as evidently shown in the figure here. So obviously, we need a different PDF to fit the daily return distribution, something with more conspicuous peaks. Here, we will try the so-called student's T distribution, which is known to have heavier tails and sharper peaks than normal distribution, though with a similar bell shape otherwise. You can resort to this documentation for more details. All we need to do is pretty simple. We follow the same code as above, copy and paste. I just need to replace this norm module with t module. Of course, we need to change the parameters as well, since they are different now. Degree of freedom, location of center, and scale. LOC is really just the mean of the distribution. When generating the PDF, we need to change the parameters as well. Let's change the title to reflect the degree of freedom and LOC. Okay, now we have everything. Shift and enter. I forgot to change the name of the parameters in the title. Should be degree of freedom and location. Run the back, sorry. It's not a Greek symbol anymore, so we don't need the backslash sign here. Here we go. Note the location of center here is similar to mean. While the higher the degree of freedom, the closer the student's t-distribution is to Gaussian distribution. What do we see? At the first glance, we see students' t-distribution can represent the daily return distributions much better, right? We don't see the peaks piercing the top or large empty gaps on the tails. We can do the same for the indices. Let's copy what we did above and paste it here. And then let's change the norm to t and update the parameters. Actually, let's just copy what we wrote above. Okay, and change norm to t and update the parameters. Let's also copy this formatted string for the title as well. Here we go. Actually, we should update the comment. Again, the fitting is pretty fast, as you can see, almost instantaneous. Pretty good fit by eye, aren't they? Here, we didn't go into the details of the properties of students' t-distribution, which we'll leave to a video in the future. But we can see by eye, it appears to be a better fit to the daily percentage return distribution than normal distribution. Alright, we have looked at some basic statistics of the FAANG stocks and some equity indices of all baskets of stocks. There are other important statistics, especially in portfolio analysis, such as skew, Sharpe ratio, sorting node ratio, and beta, one of the main parameters in the CAPM model. There's also black swan type events, which are critical in risk analysis. Besides students' t-distribution, is there another PDF that's good or even better fit to the daily return distribution? What about the Laplace function? And how do we determine which one is a better fit in a more quantitative way? In practice, do people actually use these functions for daily returns? Or do people use something more complicated? You should do some research and try to answer these questions. You may have heard of stochastic volatility model, some even with jumps. These will be some topics we will explore in the future. Okay, I hope you find this demo useful. Thanks for watching, and I hope to see you again next time.